Okay, yeah, thank you very much to the Queensland Tailing Group from bringing me here to share this with you. And thank you very much for all of you for not going home right away after work and hearing what I have to say. So, well, I want to start just by saying that what you all know, that tailing facilities are important, are necessary, and the vast majority of them are safely engineered thanks to the work of people like you all over the world. But sometimes there are exceptions to this state, and this is one exception. No, I mean this is an image that you probably all recognize. That's 6 years ago on a summer morning in Brumadinho, and 15 seconds later, the catastrophe was ongoing. No? So that was, I suppose, very impressive for everyone that was with an interest in either tailings or geomechanics, really, because what happened there? No? So when 8 months afterwards, we were contacted by the Brazilian Federal Prosecutor Office because they had made an agreement. They had several agreements with Vale, who was the owner of the facility, in which the technical police that was providing evidence for their work felt that they needed some help with the numerical modeling, really. They wanted to be trained, and they wanted to have a model that they could understand and control on their own. So initially the task was to create a tool that will help the prosecutor office to understand the technical aspects of this failure. No? And particularly, I mean, how and why it had failed that day. So that commission came with some strings attached. For instance, we were meant to use a particular finite element code, which was Plaxis, and the reason was because that was the one that was familiar to the police. Then it had to be peer review, and they selected their reviewers. And then there were things that were not in the contract, but happened and were important. No, I mean, one of them is that other studies had been commissioned by Vale on their own, and one was the expert panel report. The expert panel report came out like 2 months, when we were 2 months into our study, and that was very helpful. And I will refer to that often because it had exactly the same remit. And there was also another study which was more of an organizational nature about how things, if anything, had been wrongly organized within Vale, I mean, and what they could learn. But they were sometimes touching on technical issues, and it was helpful, you will see. Our work was, well, started, and 3 months later we were closed at home because of the COVID pandemic. And that was, in some respects, you will see, a blessing in disguise, because we had, in a sense, less distractions. And also because we were given more time to work on the basis, and we didn't have to travel to Brazil as initially planned, etc. Anyway, the report has, since it was released in August 2021, has been available on the internet. And also, well, I mean, before I go into the contents, I need to mention all the team that was involved. Mainly Professor Antonio Jens, my colleague, was the co-author, and then we had support internal to UPC, Daniel Tarrago, Luis Monforte, Nieves Lantada. There was the engineer, the policeman engineer, Leonardo Macedo, that came at the beginning to Barcelona, and he was instrumental in us understanding some of the monitoring data, for instance. And then we had also external support, Miguel Manica from now at UNAM in Mexico, and the team led by Professor Viana de Fonseca in Porto. So this is how the talk is structured. I will first give you an overview of how was this dam that failed, what was going on the dam before the failure, and then we will move into the work that was done to try to understand this failure that has two sides. One is about material characterization, I mean lab and field, lab testing that we did, field testing that was done, but we had to go through, and then all that was to fed into a numerical model, and then what we did with the numerical model to try to answer our question. So Dam B1 at the Corrego de Feijão mine, you have, this is Minas Gerais, Belo Horizonte is here, not very far from Belo Horizonte, is this region in which there are many iron ore mines. This was a medium-sized iron ore mine, and had been exploited now, well, started 50 years from now, mid-1970s. The dam itself had a 40 years history of use, and it had closed in 2016 for two reasons. I mean, one, that the whole operation has switched to, they have introduced filtering at the end of the process, so they didn't need any more a conventional tailing storage facility. But it's also true, and this is in the report from the CEA, that there were already concerns about this facility. I mean, they knew that it was full of potentially liquefiable material, and that it was not a good idea to keep on raising that. So at closure, the dam was 700 meters along the crown and 85 meters high, roughly. And if you see this section, well, the average slope is like 1 to 3, so rather steep for a tailing facility. It had been built by the upstream method in a history. Well, I mean, you had maybe some attempts here at the beginning to switch to something else, but mostly was upstream. It had this feature, the setback, that had been introduced in the mid-90s. There is no enough engineering detail of what led to that, but there are some indications that at the time it was already, well, decided that it was not stable enough, and that was an idea of if we push it back the next race, that will improve, because you're essentially decreasing the average slope. No? The one disgraceful feature of this dam was that all this lower part had very poor drainage. Some of the internal drainage elements that had been designed on those initial races had clogged. For instance, because they were using some feed, sintering feed, some byproduct of the iron ore that tends to clog, or because they didn't do enough quality control. Whatever the reason, all this lower part was very poorly drained. How it had been filled? Well, by wide space spigoting. And you had this photograph from 2002. You see here this kind of sort of radial beach around the spigoting point, and you can also see that, well, there is a pond that is getting close to the wall, no? In this area, no? You have here that switched at the end, in the last decade, to spray bar deposition that was a bit more uniform and allowed better control, I suppose. The average racing speed was about almost 2.5 meters per year, but of course it had its faster and slower periods of racing. The dam had not always belonged to Vale. Vale got the mine and the dam in 2000 and a little. This is when the setback had taken place, and this is when it closed, and 3 years almost before failure. And I have also indicated here the CPTU testing campaigns. I mean, the first one that took place 2005. And, well, I tend to interpret this slowing as somehow related to the fact that they were acquiring better data, and there was a better understanding in that period already of the meaning of that data, no? Plus other things that were happening in Brazil, of course. Okay, so that was the dam. And what happened between 2016 and the moment of failure? Well, one of the main activities that took place was to improve the pool situation. I mean, they improved the runoff control measures. I mean, this is and they did drain the pond. So you see, I mean, July 2018, the pond has been reduced to a minute amount here. So all that was, and there was also improvement on drainage at the face. All that was not useless. In the dam, there had been, I think, up to 100 piezometers and water level indicators. In the period 2016 to 2019, there were 25 that had complete records for that period. And if you look at them, they are indicative of a dam that is little by little getting drained, particularly above the setback. Below the setback, you had that problem that you didn't have really good drainage to the front. No? So still, it was going down with little ups and downs that maybe you can time with the rainy season. Anyway, that was not really fast enough, and because the idea was to dismount and this dam and also recycle the material that had been accumulated that, as you will see, was full of iron. But with all that much water inside, it was impossible. So there was this idea: let's try to speed up that drainage. So how to speed up the drainage? I mean, there were some computations about doing wells and pumping, but it's very difficult to pump something that is made of fine silts. Plus, you need to enter into. So they tried this, deep horizontal drains. You perforate from the front of the dam. The idea is that they will be 100 meters long, and once working, they were meant to extract this amount of water per hour that will really draw down in 1 or 2 years, you will have almost a quasi-dry dam. But that engineering didn't work. The perforation, you know that, I mean, perforating against a high water table in silts is not easy. And so when they abandoned this, I mean, they had only installed 14 drains, the average length was 50 meters, and all those drains that were installed, they did never extract a fraction of the water that was planned. And also, I mean, you know, this thing here in red, that was the last drain that was installed. And the operation was abandoned, not just because it was simply difficult and being not very efficient, but also because they had a big scare. And that was related because when they were installing the what then proved to be the last horizontal drain at the beginning of June 2017, they had an incident, an outflow incident, that suddenly water and mud was coming out of some of the drainage points in the face. There was then they checked the piezometers. There had been a jump in the readings. You will see that it left also a trace in settlements. And as a part of the study of the EPR, they had localized the seismic traces that incident left out. And now I think that probably my understanding of this is that it was an event in which a liquefaction started, but somehow stopped. But of course, it was not reassuring. So they totally stopped then the idea of keep on installing drains from the face, no? So what was left to be done? Well, as I said, it was not a mystery by then that the dam was full of potentially liquefiable material. I mean, there were limit equilibrium analysis that when, for instance, here you have less than 1.1 with what is meant to be peak and drainage strength. Probably is a bit underestimated, but still, I mean, the results were not comforting. No? So what was to be done with this dam? There was a very good review panel for all the critical dams of Vale, and they did consider Brumadinho several times, one of them 4 months before the failure. And at that time it was already, well, I mean, the drainage thing had not progressed as expected. What can we do? The plan was, let's acquire more data, because we need to understand better this thing before getting on, I mean, designing the remining. No? So let's do more site investigation, more CPTU, that's the last campaign, seismic dilatometer, that came handy later, more instrumentation. Apart from the piezometers, there were inclinometers that didn't really measure anything. But there were also some survey monuments on top of the dam that here you have the settlements since the dam was closed and up until failure, no? And you know, I mean, it's not big really. I mean, 1 centimeter of settlement for a dam that is almost 90 meters high. You're almost really within the elastic limit for silts. There is this more agitated period here, and this is where the DHP, where the drains were being installed. Our interpretation of what we see here is that there are more graphs in the report that support this, is that initially there is a bit of settlement, most likely because they were having, and there are indications also on the construction reports, they were having a bit of volume loss, over excavation when you're perforating your DHP. So, and that was, conducive to have a little bit of motion downwards in the face. And you see here there is a jump. And we interpret that as the fact that because the perforation operation was not going well and you had a lot of material coming to the face, someone said, okay, let's increase the pressure a bit. Yeah? So let's pressurize this while we're drilling. So I mean, that left a trace on the motion. So you have a bit of raising. But then that pressurizing led to the incident of DHP-15, and you have this sudden several centimeter settlement of the whole crown of the dam right after that incident. But that incident, all that excitement happened 6 months before the failure. And in the intervening 6 months, you have there the measurements. Nothing happens. Nothing happens. No motion. The dam was not being followed by satellite, but after the failure, people did look in minute detail at what INSAR had to say. By the time we did our report, there were already, apart from that of the EPR, there were already at least 5 studies that had looked at different satellites at different periods. The one that we like more of those that were available to us was one done in Canada, Holden et al., because they had looked at all the satellites. I mean, it was the more comprehensive in terms of coverage in time and in number of satellites that they had analyzed. And also, we thought it was it had some attractive feature, which was that they computed the signal-to-noise ratio for every single satellite stream. And this is, to me, a very revealing plot. The code they use means that blue is where you have a proper signal. I mean, they are looking at line of sight displacement, and the green is at the other end of the spectrum when the noise on that signal overwhelms overwhelms whatever is there. You don't see anything else but variability, Brownian motion or whatever you call it. No? Where there was a signal, what INSAR is telling us that the dam was consolidating at the rear. You had here about 70 centimeters of settlement in those years after closure, and here a bit less, well, much less actually, about 9 centimeters, and this was almost already finishing, but I mean, here you had the slimes were slow to consolidate, no? So this is one aspect of the EPR with which we wholly agree, which is that despite the extensive monitoring that was available for this dam, there was no anything indicative that failure was going to take place on that day. I mean, nothing actionable, nothing. But failure did took place. That's to other audiences less expert than you, I always include here the video, but I'm sure that you all have seen that. There is another video of a camera that was placed at the rear of the dam, and this is exactly the same instant in which you say the whole breakout, and it's interesting because it indicates that the higher embankment falls down almost simultaneously along several hundred meters. And you have this vertical displacement downwards. No? Anyway, the dam fell, and we were commissioned to study that. So the failure was almost exclusively through the tailings. I mean, one thing that the work of the EPR had clarified very well was that the foundation material and gneiss saprolite had not been affected by the failure. And it was strong and latent, so it was logical that it wasn't affected. The embankments, the racings, were either compacted saprolite or compacted tailings, but they had very little intersection with failure. So they were secondary. Everything was about the tailings, really. In the tailings, I mean, you can also call tailings the slimes. That's slimes, we call slimes those tailings that were plastic, that had more than 20% grain size distribution clay size, and those were really at the rear of the dam. They are involved in the run out, in the flow slide that took place afterwards, but not in the initial failure. Now, what was the lab data that was available? There was, well, this dam had been there for 40 years or more, so there was quite an extensive amount of testing, but pre-failure testing, well, the main objection that you can put to that is that it was unsystematic. It was not guided by any understanding of the mechanics of tailings or anything. They hadn't even, at some point, they were even convinced that the materials were dilative because triaxial they were showing dilating behavior. It was likely sample densification, but well, some useful data, but not very much. It was different. I mean, of course, the EPR, they knew their mechanics and they had done a better work, but there were some things that were missing. For instance, you will see there were few undrained tests, undrained triaxials on the contractive side. And rate effects, they had been very lightly investigated, and it was a possibility that they had played a role. And also the tailing sampling had taken place in a very narrow location. So because of all those reasons, we decided that part of our study had to be spent into acquiring more lab data. No? So this is a part that we subcontracted to our colleague Viana from Porto. He went to Brazil, and he went really deep into the remains of the dam, probably because he was hand on hand with the police, and the Brazilian police was not going to be scared just by the possibility that that thing was unstable. They were probably used to more dangerous things in their day-to-day activities. So they went deep into the dam and extracted some block samples that fed into our study. Now, what are the tailings of Brumadinho? I mean, they are not very different from most tailing dams that probably you have experienced. So sandy silts to silty sands. Those are the historical grain size distribution. There were many of these, and this is from the EPR. Those are the slimes you see on the fine end, and those are different samples, are coarse, fine, the ones that we came up. I think it's more interesting perhaps to have a look at these. From the block samples, no? Those taken at different depths. You see this sub-centimetric layering, several millimeters, sometimes a centimeter, change the color. I mean, this is also a very common feature in many tailing deposits. Now, that has important consequences for testing, no? Because even if we have the luxury of block samples from the bottom of the dam, the moment they appear like that, you have to take one step back and think, am I going to test that? Every single specimen will be different. So it will be very difficult to make general statements. So we took the decision of saying, no, of course we will test something like that, but what is more important is to create materials, reconstituted materials out of the tailings. Model materials, if you wish. Because if you insist only on testing intact specimens, every single specimen is different, and you cannot really generalize what you see. Whereas if you create something by the same procedure, with the same characteristics, at least you're testing something that is in the dam. And then we will come back about how that material that is in the dam, but is not as it is in the dam, can be related to what you see. Anyway, the procedure that was a decision also that was taken by the EPR. So you homogenize the material, you moist stamp them into triaxial specimens. Interestingly, in the selection here, we took a different route. I mean, the EPR had selected their model materials to cover, if you wish, the D50 range that you see on the historical samples. We took a different approach in which we said, okay, we're going to follow color. So you separate the black tailings, the red tailings, and the brown tailings. That is not as arbitrary as it seems, because color is a good proxy for iron content. So in principle, yeah, I mean, we did guess, and then it turned out to be that, for instance, the black color tailing was the one with more iron. It had 90% iron oxide, and this explains this huge specific weight, 5. And selecting by color, we sort of cover all the specific weight that was available in the historic range. If you select by D50, well, maybe you don't, no? It was more of a surprise, but that came handy as well, that also these materials that had been selected by color sort of span correctly the coefficient of uniformity, the slope of those grain size distribution curves. That is something that we didn't expect, but then it came to be. No, I mean, those are the 3 materials that I don't know which one is the black one, which one is the red, but they sort of cover the range of coefficient of uniformity. Anyway, you start testing them, and this is one of the aspects in which the pandemic came handy, no? So the lab work at Porto included physical characterization, isotropic, odometric compressibility, bender element testing, permeability, and then lots of triaxial testing. Really lots. I mean, those are the ones that at some point, why? Because in Portugal, they were allowed to work in the lab while during the pandemic. Everything was closed, but somehow they were classified as a construction activity. So and of course everything else was closed. There were no restaurants, there was no shops, there was nothing. So they were testing and testing and testing. And at some point, actually, we had to tell them, well, bring us what you have already, because if not, I mean, you're driving us mad. No? They were looking obviously for critical states, because one thing that was obvious was that this failure was one failure of flow liquefaction, and if you want to understand flow liquefaction without using critical state soil mechanics, in my opinion, you're doomed. There's no way, or not practical way. So, okay, critical states. You know, critical states. I mean, there is a friction angle. The friction angle was not. It didn't vary very much. I have here some results from different batches of our study from the EPR. About 34 degrees triaxial compression. Most of them. That's not a surprise. Many tailings have those numbers. Where there was more variation was on the position of the critical state line on the compression plane. Not so much in the slope, rather more on how high it is. And that was an interesting feature, of course, because the higher you are, the more dilatant space there is for that material to be in, and the lower you are, the more contractive space there is for that material to be in. So it was for a while we did try to figure out if there was one parameter that will correlate with that position of the critical state line, no? And we did several attempts. The one that while doing the study, so nothing with the D50, not really specific gravity, coefficient of uniformity a bit better. The one that was working better at the time was Koseny-Karman permeability. Koseny-Karman permeability, which is an estimate. We're following a formula by Chapuis, in which, we're always assuming to normalize that void ratio is 1, because actually that's the average of void ratio from the block samples that we had. And essentially, Koseny-Karman is, here you have specific surface that is computed from the grain size distribution, because this is not a non-plastic material. Actually, the thing that correlates better with that position of the critical state line is a specific surface. So we should have used that instead of the permeability, but I didn't make this plot until coming here to Australia. So this is a novelty for you. But anyway, that gave us some understanding about what was important for the critical state position, that, as you know, given a particular density and confinement, will also control the residual undrained strength, which is an important feature. No? But it's not everything about where the critical state line is. What is also important is how you go to that critical state line. And that was coming again and again from the lab testing that we were doing, that those Brumadinho tailings, I mean, if you have the patient of following them to the bitter end, they will liquefy to almost nil undrained residual strength, going through a peak before, so they were really, really brittle. Now, the peak undrained strength is also something important in the calibration of any model, in any kind of a study of stability. Here there was one aspect in which we did improve from the EPR. The EPR had very few tests on the contractive side, and they have interpolated them, and some that are not in this figure, that are on the dilative side, that continues up to here, as a function of the compaction or initial state parameter. No? However, after many more tests were done, it was pretty obvious that that was not, initial state parameter was not the main control on undrained peak strength. What was more relevant was the consolidation path. You have here the, I think those are the isotropic, and those are the anisotropic consolidated. That was what was making the big difference, and that was something also that had been observed in other previous tailing studies, like the one that Andy Fury did in Marysprut, etc. So yeah, I mean, prior path to consolidation was the main control on the value of normalized and drained peak strength. As for liquefied, well, you had many tests here at very low values, sometimes higher values, but that, in my opinion, has more to do with how some tests, for other reasons, were stopped too early, or there were some incident while testing, so they had to stop the test. No? So there is less, I don't put much weight, really, on these things here being relatively high. No? There was a dedicated study on rate effects. We were, for the 3 batches of material, say red, brown, black, we did a series of anisotropically consolidated and drained shear at different rates, in which you were multiplying the shearing velocity by 10 times and by 100. What you expect is that if the material is really has some propensity to have rate effects, that will make a difference to the response. And there was very little difference, and it was unsystematic, really. In the only one that at least it was increasing from the 1 to the 10 to the 100, it was about 2% per log cycle, which is very small. And this was not really a surprise, because, as I said, the tailings were not plastic. And if you go to I don't know, in principle, this is correlated with plasticity. Well, it is true that there was a test in the EPR where they had obtained some evidence of creep. Now, that evidence of creep, later work has put that into question, because I mean, the way that the test was being carried out was with external displacement measurement, like they were using, as we were using, as you do when you're testing tailings according reconstituted tailings, using oversized end plattens, and those oversized end plattens are typically lubricated with grease at the ends, because you do that to avoid localization. And so there was an interesting study last year by David Reid. He took a block of steel, he applied different layers of grease and he measured creep outside the cell, yeah? So the same procedure, and he obtained creep results that were of the similar order of magnitude. So you can, after seeing that, I started to think that maybe there was what was interpreted as material creep was maybe an artifact of the testing arrangement. There is another issue in which we disagreed with the material characterization that had been carried out by the expert panel report, because there was it was emphasized that the tailings appear to have some bonding. And that is a more complicated discussion. I won't give you all the details about why I think that that's not correct. I will just give you what was for us the main evidence indicating why there was no bonding on these materials. And that was based on the measurement on the properties of that control shear wave propagation, elastic shear wave propagation in geomaterials. There is this classic formula in which you have that the shear wave propagation it depends on the mean stress on the propagating plane, no? And the effect of stress is controlled by this exponent beta, and the average, if you wish, is given by alpha. And Carlos Santamarina has been studying this for the best part of 30 years. There was this experiment at the origin of his, one of the first things he published. He was saying, okay, well, I'm using Bender elements in the lab. This is a sand, it has its beta, it has its alpha. If I cement that sand using Portland, what I see is that increasing confining pressure has almost no effect on shear wave velocity. Why? You can understand that from a micromechanical point of view, because if you have cemented the sand, you have fixed the contacts. So there is really no deformation. That minimal deformation that takes place when a wave is propagating is not really, it's not affected by the confining stress, because the contacts are always in the same configuration. That is more or less the explanation for that. Anyway, apart from doing this experiment, then he started to do many more experiments, recopilating, because he observed that alpha and beta are inversely related. And that's a correlation. So the stronger stress dependency is that observed in clays, it's a bit less in sands, and in cemented materials there's almost no stress dependency. So, but instead you have faster waves because they are cemented, no? So, that was a database that had been compiled during, as I said, 20 years of work. So, and we could compare the results of Brumadinho to that database. I mean, there were shear wave measurements in the field that you could put as hard in form, just by looking at what was the density at the different depths. And there were also Bender element testing, no? So you can get alphas and betas for different reconstituted materials. Where did they plot? Here in the middle. Where do you expect them to be? They are silts. between sands and clays, and very far away from anything cemented. So no bonding. But it's not just lab testing. You have to consider in situ testing results. The Brumadinho case is one exceptional because of those that have involved big failures. They had a substantial amount of in situ testing before the failure. For instance, there's almost a kilometer of CPTU that had been acquired before the failure. There are also other tests like the seismic dilatometer that I was mentioning now. No? Let's focus on CPTU, which was the one that was more useful. And if you plot we did clean the data, there were errors, blah, 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 but you ended with 37,000 points related to tailings, and they plot a bit all over the place in this classification graph. So it's important to try to separate that into some groups. No? And those were the groups that we selected for analysis. No? We were going to distinguish fine CPTU fines, those in orange, and CPTU cores, those in blue. The limit between them was established at a particular value of soil behavior type as computed per the Robertson and Wright formula. That particular limit was established by looking at what different soil behavior type limits, what was their effect on another property, on pore pressure generation. Yeah? That value was the one with best discriminating power, in that the coarse CPTU materials, they were such that they will have a very low pore pressure. You can assume that CPTU was drained in them, because BQ was less than 1%. In the CPTU fines, there was a bit of everything. There were some that, unfortunately, there were 20% that maybe were drained. There were some 30% that were in between. And then there were some that were out of the picture here that were really, really undrained. No? So everything that we are or certain that is drained is in the cores, and here you have undrained and partly drained behavior, and maybe a bit of drain. Now, once you make that distinction, you can analyze separately using correlations or interpretations. You can analyze separately the properties of the CPTU fines and of the CPTU cores. For instance, that was this is a result of looking at dissipation tests. Dissipation tests were only available actually on positions where we have detected CPTU fine, of course, because you don't carry a dissipation test if you're not actually observing some pore pressure in the CPTU. You only stop when you are observing pore pressure, and then you can wait until it dissipates. And that gives you a value, T50, that you can translate into permeability. And this is what we're doing here. We are presenting the results of the permeability estimates that were obtained by the dissipation test on the CPTU fines. Now, on the CPTU cores, you don't do dissipation tests, but those of you that were with me yesterday know that there is one alternative way of estimating permeability without stopping the penetration, which is known as on-the-fly interpretation. You just look at the generated pore pressure, and that gives you an information of permeability. And this is what we do here for all the coarse Brumadinho tailings, and this is the distribution of estimated permeabilities that we get. And the point of this graph is that, hey, it seems that 1 to the minus 6 meter per second is the limit of permeability between CPTU fine and CPTU coarse. That will be useful later when when we try to tie back field observations with lab observations, because remember, our lab observations are on reconstituted materials, things that do not really exist in the field. Anyway, still, and before going to that, it's worth stopping on some results that came out of, making that distinction. I mean, for instance, there is one set of correlations by Olson and Stark to estimate normalized and drained peak shear strength and residual and drained peak shear strength. And those are independent of permeability, independent of drainage. So you could apply that to both groups, to the fines and to the coarse. And it was pretty obvious that the fines were worst. Yeah? And they were really bad. No? I mean, this is the lower limit of the correlation. I mean, you cannot get a lower number than 0.03 if you use that correlation, because the way it was established. And the fact that you have almost 50% of your values at the lower limit was sort of suggesting, it might be the case that if they are pushing the boundaries, no? They are really bad. No? Also, for instance, a state parameter, and the way you can estimate that with the method of Proust or with the widget, say, using Norsan, and those were the curves for the fines, those were for the coarse. So, I mean, the fines were catastrophically bad. Very, very high state parameter, very low strength, and the cores were not that good either, because actually, I mean, if the dam had been only of cores, I mean, the usual criteria is that you design for the 80% percentile, and that will be still something that is contractive. But the fines were very bad. So it was important to figure out where are those fines. Where are those fines in the dam? And we can tell that by exploring the information, the spatial information on the CPTs. And the way we proceeded was, okay, this is the distribution, the plan view of where the CPTs are in the dam. So let's create a grid in plan view that has, well, at least a decent amount of CPT in every square. Every square that comes out of having these sections and alignments, no? And then that grid is projected vertically, taking into account the stages, the different construction stages, because it was also obvious when you were looking in detail at the CPTs that the racings left their mark. You have, for instance, here, this change in behavior. It coincides exactly where you can guess it was the limit of the dam when they raised the stage. And that is logical if you think the way it was built, by having this wide space spigoting, because when they were raising, they will probably change the point of spigoting from one point in the dam to another. And this is what is, so it made sense to create like a grid of blocks, if you wish, like a Lego, that was organized as a guided by the CPTs in plan and guided by the racings in height. And that, you could analyze that in detail, say section by section or alignment by alignment, and work out what was the percentage of those very bad fine tailings. Where were they located? For instance, here there is 100%, awful. Here there is nothing, great. And there are all sorts of numbers in between. No? At this stage, you need to remember, this is not just for the fun of it. We want to do a model to analyze the dam. So there is a necessary simplification here. You cannot have 25 different materials. We don't know how to do that. So we decided, okay, because fines it has been proven in the lab that they have, not in our testing, in other people's testing, they have an overwhelming influence in soil mixtures. We're going to move from CPTU fines to fine tailings for our numerical model when you have more than 50%. But coarse tailings, we will only consider coarse when they have less than 10% CPTU fines. And everything that has between 10 and 50%, we call it a mixture. And then at the rear, the slimes. Okay. I just want to comment that you will see here a lot of red in this relatively high position and relatively close to the wall. There were some photographs indicating why there were so many fines there in close to the wall in higher positions, because in later stages they have had too much water. Anyway, that's all that I have to say about material characterization, and now I'm moving to the numerical simulations. For the numerical simulations, you need a good code. We had Plaxis that was in the contract. Then you have a constitutive model that is relevant for the behavior that you want to simulate, and then other things that I will explain later. The constitutive model that we were using was CASM. We had CASM is a relatively simple elastoplastic model that incorporates the state parameter, and we selected that because originally it had been designed, among other things, to represent flow liquefaction, this undrained brittleness. So it did seem relevant. And also it had the advantage that the way it is formulated, it was very easy to extend to viscoplasticity, because we needed that, because at that time, well, there was still the possibility that creep had played a role in failure. No? CASM, the yield surface is like that of Camp Clay, if you wish, but it has been generalized, so depending on how you select these numbers, you can have a more peaky yield surface that will give you higher undrained peak strength, and you can select that the intersection of critical state with the yield surface is closer or farther away from the pre-consolidation pressure, and that in a sense controls very much the level of residual undrained strength. Anyway, it seemed appropriate, and also, as I said, it was easy for us to manipulate CASM and add an element of viscous behavior, just in case you see that creep was an important effect. No? So now we had something in which we could verify that as well. No? CASM is not the end of it all. I mean, it has some limitations. For instance, it does not have an isotropy, and if you're calibrating and there is that huge difference, for instance, in peak strength between isotropic consolidation and anisotropic consolidation, you need to make a selection and say, oh, okay, I'm going to calibrate with the anisotropic consolidation because that is more like what I have in the dam. The parameters, well, that's not there are 7, and that's what I was trying to say. I mean, you can, what is also interesting of CASM is that you can fit your parameters with triaxial test results, but you can also relate them to things that you can measure in the field, like the peak normalized undrained strength that I was estimating with the Olson correlation, or the state parameter that you have at least some indication with the plus method. We know that is too much, but at least we have some indication, no? Or the at-rest coefficient that you can get from a DMT. To connect lab and field, I have made the point that our cores and fines in the field were separated by a certain value of permeability. You can compute permeability using Kosenik-Karman for every single sample or material that you test in the lab. Also, we did actually calibrate and verify that this Kosenik-Karman formula was getting the right results, because we did measure permeability independently. So, one observation at when we had to actually put numbers into the model was that even our finer materials, or the ones that were less permeable, were not quite the finer ones that could be found in the dam. That was important because sometimes we said, okay, let's make some parameters even a bit worse that we have seen in the lab, because potentially we have even worse materials in the dam. It was also useful to have the ability to simulate the CPTU using CASM, so we could verify that exactly that the permeability limit that separated no generation of pore pressure for generation of pore pressure was this 10 minus 6 that we have taken up from the interpretation of the CPTUs. No? Now, we have our, you go to bed one day and the next day you have to put numbers on the computer, and okay, those are the numbers that we're going to put in the computer, and we're going to run something to see if we can find what happened in Brumadinho. No? We also needed some hydraulic flow properties, like, for instance, water retention curves. Those, thank God, they had been measured by the EPR, and we could just fit our expressions to the results they had. So we had, our model ready to compute. And the first thing we did is what we call reference simulations. Reference models, they are plane strain models, you see, 3 sections here. Why plane strain models? Well, to begin with, because it's easy, relatively easy. But also, I would like to point that if you look at this, the way this thing failed, well, you know, it's not very 3D. At least that front is moving all simultaneously at the beginning. No? So why not plane strain for starters? Let's see. We build those 3 models with all these Lego pieces here: red, green, yellow, fine, medium, coarse. And we had for the tailings CAS and sometimes CAS Visco, other constitutive models for the other materials, but they were relatively unimportant. First thing that you do is that you raise your dam. That we were adamant that it was important to raise the dam using exactly the same model and the same numbers that you are going to use later to analyze triggering. Why? Because that lends credibility to those numbers. I mean, you might have put something that is just too weak. If it is too weak in raise number 3, it will fall. You are not arriving to 2016, let alone 2019. So, and there are very few data here. I mean, this is one of the few things that you can verify your guesses against. The dam is there before that fateful day in January, no? So in those races, we were using the lagoons extent, hydraulic conditions such as extent of the lagoon that was well detailed on the CPS, and the average rainfall that had been recorded at the dam, no? And so once the history is finished, you can at least verify some things, apart from the fact that the dam hasn't failed and has been built. For instance, you can verify settlement at the rear, because INSAR has told you something that you can trust there. There were 70 centimeters. In the model, we did get 60. So, okay, not perfect, but we're there. No motion here at the front. What about pore pressures? Pore pressures are very important. So this is the end situation. You have pore pressures before failure, contour of pore pressure 0. It has this funny shape in this section because this material here is way more permeable than the others that surround it. And this is the degree of saturation. Well, you can extract from those results pore pressures at the piezometers at that particular moment in time, or pore pressures after dissipation on a CPTU. After dissipation, you get the the reference pore pressure, the pore pressure that is there in the field, and more or less they were fitting well. So another reason to believe this reference model. And now we have a tool with which we can investigate what happened. When you go and read the basic literature on flow liquefaction, you know that there are several things that we can do as engineers. One, figuring out if a material is susceptible to liquefaction, and then once we know that there is something susceptible to liquefaction, trying to investigate what will trigger that thing into liquefaction. There are many possible triggers. You can you have all these schematics and drain loading. You raise, pore pressure increase because you're raising your water table, for instance, drain and loading, etc. Now, what is the problem with Brumadinho? Is that if you go at the catalog of possible triggers that had been identified prior to this, well, load increase, believe me, that dam was quiet. They were not raising it since 3 years ago. There was no construction activity. Cyclic loading, there was no earthquake that day. And the blasting that there was too far away in time and space, and not any different than the one that had been carried out systematically during all the life of the mine. And loading, erosion, overtopping, it was a sunny day. Foundation failure, nothing failed at the foundation. Internal erosion, that was our best hope for a very long time. You know, this photograph here, there are a bit of black tailings coming out of this tube. Unfortunately, that was that comes from an inspection report one day in June. They were doing inspection reports weekly, and it never ever occurred again. Was that evidence from June enough to explain, to justify internal erosion? Very dubious. Water table rise, no, it was going down. It was going down, so yeah, bad. Our presidents, the expert panel report, facing this, they have gone with an explanation based on creep and loss of suction due to intense rainfall. We didn't really thought that was a good explanation to begin with, because at that time we had already done the experiments and there was not much viscous behavior. And also, if you look at the rain gauge at the dam, well, it turns out that the last years were about those of the dries on record, no? And actually in Minas Gerais, climate change is such that in Brumadinho, I mean, you have less rain in this period, no? So still, once you have your model, you can start playing with ideas. And you can say, okay, I know it didn't rain, but what would have happened if I throw lots of rain since closure? Imagine that the last 3 years before closure were as rainy as the most rainy year in the history of the dam. And what the model said that will happen was that you will fully saturate the dam, and then it will settle a little. No instability. Okay? So that's not a good explanation then. What about creep? As I said, we have experimental evidence that there is very little creep. But just for the sake of it, we're going to introduce numbers that will result in a large amount of creep. Well, the effect of doing that is that what we call the extreme creep scenario is that you delay consolidation a lot. So in the last 3 years, you get a pattern of settlement that is not the one in INSAR, it's something different. But nothing in terms of instability at the face. Actually, in a separate study that I don't have time to enter into, we did explore the idea that if you were to have viscosity, that is actually of some help for triggering, because because viscous behavior acts as a damper. And if you have a sudden event, that will maybe give time for drainage to come into your help. Anyway, another explanation that we couldn't believe. So what? Well, these people of dealing with organizational aspects, the CEA, they were not geotechnical engineers, but I have to recognize at this time that they were not silly. They were looking at this photograph and they were saying, okay, you know, the only activity that day in the dam was that someone was drilling a borehole. And that borehole, if you look at the pattern of failure, well, is suspiciously right in the middle. Could have been a borehole. I mean, the EPR had discarded that, and the first time that the policeman told me, what about the borehole? I said, you don't know anything. I mean, it's impossible. A borehole the size of my hand cannot destroy a dam 700 meters in Coronation. But at this stage, we were pretty desperate. So, okay, let's look at the borehole. How was that borehole drilled? The moment you start looking at the borehole, one thing is curious, that borehole was one of the two that had been deeper in the whole 43 years of history of the dam. So they were doing something new. You always know as an engineer when there is something new, there is a small possibility that it might go wrong. The kind of borehole they were drilling, because it was so deep, they were using wireline drilling, and they were sustaining it, they were circulating water. No? Also, no special caution, there was no recording of pore pressure, and sometimes, you know, a wireline might get stuck, and the way you get it out of that stuck position is by increasing pressure, and that was hand operated, so, you know, it was an operation not very controlled. And that was even more important. At this time, we already had our simulations of history, no, of the dam. So when we draw the position of this borehole here, it was pretty evident that they were drilling through almost 30 meters of dry ground and then into saturated soil. That meant that because they were circulating water from the top of the borehole, they were increasing pore pressure by about 300 kPa. That's not a trivial amount. So we started to investigate with a separate small model of what happens around a borehole when you increase suddenly pore pressure, and the material surrounding the borehole is described by the CASMA model that we had calibrated for the tailings in Brumadinho. Well, lo and behold, what happens is that you actually liquefy. And you have this fall, this is the stress path, and you liquefy not by a large amount. I mean, you liquefy by something like maybe 25 to 50 centimeters around the borehole, not very much. In this separate study, one thing that came out as well was that for this to happen, the material had to be very impermeable. Now, that last borehole, the day in which they were drilling, were passing through these 12 meters of very impermeable material in which pore pressure, well, this is a BQ, this is pore pressure, but I have computed the BQ, this is about 1.2, so extremely impermeable. And without any, you know, the one before the last, which was similar in depth and in technology and everything, what was different was that you didn't have these 12 meters of undrained material. You have several interlayers there, no? That might have drained thing. Anyway, that was our best guess now, so let's discard this possibility as well. How are we going to represent that trigger in our numerical model? Well, a tiny area here, this is at the scale of the dam, of 1 by 3 meter high. We're going to liquefy that because of overpressure at the borehole. Liquefy means that we're going to change a couple of numbers on the constitutive model so that it's very weak suddenly. No? That tiny area, the one that is there inside the green circle. And because if it is the trigger, it has to be fast, because just watch the video, everything happens very fast. Well, we declare everything and drain. And okay, well, let's run this. There is a bit of liquefaction there. Nothing happens, oh, something happens. It propagates, and then the dam falls. We were rather surprised by this. But then started to look at the results in more detail. The motion that you have seen there is pretty much what you see in the film. I mean, like this goes down, this goes over the initial embankment. What is going on there is, of course, progressive failure. And those are your different values of undrained peak resistance as predicted by CASP. And this is your values of residual. And one bit, actually the first bit that falls down to residual, surprisingly, is this one here on the passive end. And then, you know, progressive failure is about, is falling there, so it transfers load to another bit, so that bit also falls, and so on and so forth. We could repeat this scenario for the one to the last borehole and see what happened. And what happened there was that even if we tried to trigger a failure, it didn't propagate. And that's probably due because of the different distribution of materials. That's we also tried the last drain, the one that created an incident, and in the numerics it came out that you had a bit of liquefaction here close to the face, maybe enough to justify those outflows that they saw, but nothing that propagated and fell the dam. Of course, a borehole is a 3D thing, and we were analyzing that in plane strain. So in our models, actually, we were that bit that we were activating, it was not really like a borehole, it was more like a tunnel. So we wanted to verify that this thing will work also in 3D. What we could do at the time, when the report was done, was to create a slice 15 meter wide, and this is the borehole, 1 meter wide, and you are going to do the same. Just declare that tiny volume there liquefied and see what happens, and what happens is the same. You have the same mode of failure. Still, this is not full 3D. Full 3D is another thing. So here comes my PhD student, Mohammed Ratha bin Nasab, who's spending the best years of his life pleasing me with this study. So he has, I mean, it's not easy to create a full 3D model of the dam with plastics, because I mean, you cannot create these Lego bricks and then do the meshing. That doesn't work. I mean, you break down the program. But we have been working with Bentley to move around that problem by manipulating element by element. And Mohammed has managed to get a distribution of initial state in the sections and in the cross section that represents what we believe. I mean, the same thing that we were using in the 2D. He gets the right amount of settlement, and is more like the one you see on the photographs, because of course this is 3D. And he gets the failure that propagates in the section that, as we are used to see. And now we can also see how suddenly it propagates all across the dam, which is something that we couldn't see before, and we can see now thanks to his work. Now, I'm finishing. Well, the failure of B1 was due to liquefaction. It is likely, and we are more and more convinced that it was the drilling of borehole what triggered liquefaction. They were, by the way, they were trying to install more piezometers. It is also probably, you can argue that a combination of unfavorable circumstances, the distribution of materials. I would like to put some numbers on how unlucky they were, but that will take some time. I have some ideas for that, but it will take some time. Obviously, what was not a matter of luck was the fact that that dam had been built without following principles that were well established well before that dam was started to be built. Having a well-drained structural zone, that was something that tailing engineers knew before I was born and before they started in Brumadinho. Another thing that we have that we conclude from this work is that it is very difficult, if not impossible, to analyze a problem like that if you don't use an effective stress model that can represent flow liquefaction. I mean, total stress models are not good for this. And a final remark is that, yes, triggering ex post facto, even with some difficulties, is easier than designing. And particularly because, I mean, when you use these tools, you have thrown out of the window, our friend, the factor of safety. Are those things going to substitute for limit equilibrium? I don't think so. But still, I think that they might be useful, particularly if we can manage to agree how to treat the different uncertainties that are fed into this problem. And that's all. Thank you very much.